Ora iniziamo la parte forse più densa di questa giornata, quindi invito il professor Art McDonald, premio Nobel nel 2005, a raccontarci come attraverso il progetto Aria si scopre la materia oscura.
Good morning. It really is a pleasure to be here because the successful first stage of Aria that occurred in the last month or so, that was reported to us at our collaboration meeting in Naples this week, gives us great encouragement that the science that we hope to do will in fact be successful. I'm going to try to tell you a little bit about what that science will be, and hopefully you will understand how fundamental it is to our understanding of our universe. We have great advantage here in Italy and in Canada with underground laboratories, which in Italy is in Gran Sasso, and in Canada is in Snow Lab. And I'm very pleased to be here with my colleague David Sinclair, who built the Snow Lab facility and was its founding director. David and I are supposed to be retired, but in fact we are both very enthusiastic about the possibilities for science that it is possible to do with these underground laboratories, and in particular with liquid argon and with liquid xenon, as David will tell you, that the Aria facility is absolutely fundamental for the success. What we hope to do with our experiments is to understand our universe more completely, to understand our Milky Way galaxy, because dark matter is what holds our galaxy in its present form. When you look out on a dark night, there's 5 times as much mass in the dark spaces as there is in the stars that are glowing. The stars that are glowing are made up of matter that is similar to what we are made from. We do not know any particles that we have ever observed in experiments here on Earth that behave like the particles that are creating the gravity to hold the Milky Way in its present form, that looks like this if you were standing far away and looking at our galaxy. What we see when we look on a starry night is simply a patch of stars that are more dense, and that is because it's like a pancake, and you're looking along the edge of the pancake. But galaxies that look like this, if you actually measure the speed of the stars as you move out in the radius, the ones that are in the outer region are moving so fast that they couldn't be held in that form if there was not 5 times as much gravitational attraction pulling them into this spiral motion as what is created by the glowing material. These measurements and other measurements from astronomy lead us to think that these particles are very weakly interacting, and they're very massive. And so physicists love whimsical terms. These are referred to as WIMPs. And so our whole objective is to observe WIMPs. The way we do it, since we know that they are there creating this pattern in our galaxy, in fact they are going through us right now as they go through everything else in our galaxy because they're very weakly interacting. We hope to build big detectors, particularly ones using liquid argon, and when these particles hit an atom of argon, they produce a signal. And we wish to be the first to observe them and understand their properties more completely. So we're looking for WIMPs from our galaxy striking our detectors and producing light and electrical signals. In the last 20 to 30 years, we have remarkable results from a number of experiments in astronomy that lead us to think that of the total matter, total energy in the universe, we are about 4%, dark matter is about 26%, and 70% is something that's called dark energy. That's inferred by modifications to Einstein's general relativity that imply that gravity is not always an attractive force, but in fact can accelerate things. So when you look at the far distant regions, you see stars that are moving faster than you would have expected. But in terms of the dark matter, our objective is to observe them striking our detector at the CERN accelerator in Geneva, the highest accelerator energy in the world. They hope that for the first time since the original Big Bang, they may produce these particles here on Earth. So with the experiments that we're doing, which are made possible by the Aria facility, we are making measurements that are comparable to the most extensive measurements made in particle physics today at the CERN accelerator in Geneva. We have brought together a very large international collaboration, which is based on the work that has already been done here in Italy and the work that has been done in Canada and other places around the world. We have 14 nations that have come together, over 420 scientists who are working together on what we call the Global Argon Collaboration. We have an operation in Sudbury in Canada, a detector using liquid argon that has 3 tons in it. What we are hoping to produce at Aria is 50 tons for the so-called DARKSIDE experiment at Gran Sasso, which we hope to have in operation in 2023. And our objective in the long term, and the collaboration is committed to stay together and pursue this objective, is an even larger detector of 400 tons, which will push this sensitivity as far as you can go without substantial difficulties. Because ironically for me, where we worked on neutrinos for the Nobel Prize winning work, neutrinos will interfere with this experiment when we get to the level of 400 tons. But that will be a factor of over 100 greater sensitivity than we have had today in looking for this dark matter material, and we hope that in that factor of 100 we will have the opportunity to make a direct measurement, because in fact, theoretically, the motivation for things we're looking for is very strong. This is the experiment that's now running in Canada, called the DEEP experiment with 3 tons. What is being designed at the Gran Sasso laboratory is remarkable indeed. It's building on a detector technology that has been developed at the CERN laboratory in Geneva in preparation for enormous experiments for studying neutrinos using liquid argon. But it is an ideal technology for the measurements that we want to do. And as you can see, we already have detailed drawings of how we are going to create this detector. We spent the week in Naples discussing further those details and also hearing about the great progress that is being made on this experiment, including world-leading sensitivity for observing the light using things called silicon photomultipliers that were developed extensively in the Abruzzo region and are being built specifically for this experiment. The fundamental part of it, as I mentioned, is the ability to get liquid argon that is low in radioactivity. It turns out that the atmospheric argon, the argon that is contained in our atmosphere, which is the normal way that you extract argon for other industrial purposes, has very small amounts of radioactivity in it. However, we have identified, Cristiano and colleagues have identified a remarkable underground source for argon that has been out of contact with the cosmic rays that bombard the atmosphere for hundreds of years, thousands of years. And this radioactivity, therefore, is not present. We know to at least a factor of almost 2,000 it's lower than what you find in the atmosphere itself. But in addition to this, we require further purification, and that is where the Aria facility comes in, because we have very stringent requirements for this experiment. And so the process will be to take underground argon from a site in Colorado that's producing carbon dioxide for pressuring oil wells, in fact, transport it to Sardinia, purify it in the Aria facility, as was described earlier, and then transport it to Gran Sasso for use in this experiment. The facility for the extraction in Colorado has had a tender let for that. Other countries are contributing to that process as well, and we expect to have that in operation next year and expect to have the Aria facility ready on the same time scale. Why do we use liquid argon? It's because it's a unique material for observing dark matter and not getting signals that come from local radioactivity. If you have a signal from dark matter, the light is emitted in 10 nanoseconds, 10 to the minus 9 seconds. If you have a signal that comes from radioactivity, the light comes out over a period of 10 microseconds, 10 to the minus 6 seconds, 1,000 times longer. And so simply by using digital approaches to measure each pulse that comes from our detector, we look for the ones that are short, and we can discriminate by factors of more than 10 billion against local radioactivity, and therefore we have the most sensitive detectors for this approach to measuring dark matter in the world. In order to do it, we require the properties of Aria, and we're very, very pleased to see the success of the first stage of Aria, which meets exactly what was predicted for it and gives us great assurance that when we build a full facility, we will accomplish what we want to. We also will use a facility underground in Spain to measure the success of the Aria facility by measuring these trace amounts of radioactivity. We will use the Gran Sasso laboratory. You can see where the experiment will be sited. We eventually hope to be in the Sudbury facility, where we have many other experiments of a much smaller scale looking for dark matter. It is again, a deep underground facility, a very clean one. I would like to conclude, however, by saying to you that we as scientists, hoping to understand our universe more completely, are extremely grateful to the government of Sardinia, to the people of Sardinia, for providing this opportunity for us to do these very fundamental measurements that we hope will give us very significant results. But we're also extremely pleased that in the process of doing so, as has been described and as you will hear even further, it provides new economic opportunities for this region of Sardinia. It happens that I come from a part of Canada in Nova Scotia. When I was growing up, it depended upon coal and steelmaking from that coal. That was terminated when I was about 20 years old, which is a long time ago. And the region has been finding great difficulty in being able to survive economically since then. For me, coming from a place like that, it's absolutely remarkable to see the potential here for a recovery of the coal industry with the latest in technology. And I salute the people who have developed this, and I look forward to seeing that as we work with you in the future. Thank you very much.
Professor David Sinclair, please.
Buongiorno. And that exhausts my knowledge of Italian, I'm afraid. I want to talk to you about a possible future use of the Aria facility, again, for basic science. I want you to understand that there is a history of projects needing the enriched isotopes that you've heard about in order to do fundamental science. This is a growing field. It is a continuing field. And so that's my main message to you. So I want to talk about xenon. It was introduced earlier. I want to explain why it is we're interested in making isotopically enriched xenon. So experiments in fundamental physics often require the use of specific isotopes. Isotopes are different mass forms of particular chemicals. But to a nuclear physicist, the chemistry is irrelevant, almost irrelevant. What matters is the isotope. They're all different from the nuclear perspective. So you've heard all about the need to remove argon-39 from regular argon to do dark matter searches. But quite some time ago, we had another fundamental problem to solve, which was the solar neutrino problem. Why the sun did not seem to make the numbers of neutrinos that were required. And so we built the SNO experiment, the SNO, using 1,000 tons of heavy water. Heavy water is an isotopically enriched regular water. And how was that produced? It was made by two processes. There was a specific process that took it from the tiny fraction of normal water, which is heavy, up to about 30%. And from 30% to 99.92% was done by distillation. So this is a very well-established technique for light systems. The value of the heavy water that we required, we used 1,000 tons, and that was estimated to be worth about $300 million. Then that was 25 years ago. Fortunately, we didn't have to pay that much. We were able to borrow it. But that's the scale of the cost of these experiments. There's another very high priority experiment today, which has already been mentioned. This is called the search for neutrinoless double beta decay. And that is a terrible mouthful, and understanding the process is very complicated. But what we need is a form of xenon, this isotope mass 136 we call it. And the question is, could we produce this by distillation in a facility like Aria? Well, what is this mouthful? Well, you should understand that neutrinos, they sound very esoteric and so on, but in fact, they're the most abundant particle in the universe by a huge factor. We think there's probably 100 billion times more neutrinos than there are electrons and neutrons and protons, the stuff that we're made of and what we understand. So we're talking about the basic universe here. What we discovered with SNO was that these particles have a tiny amount of mass, but we don't know exactly what the mass is, and we don't know how it gets this mass. Why do we have a class of particles which are very much less massive than the things like electrons and protons and neutrons? And there is a mechanism we know of that could give them mass if they have a particular property, which is that they are their own antiparticle. Now, particles like electrons have antiparticles, in this case the positron, which we're somewhat familiar with. All particles seem to have antiparticles, but maybe the neutrino is its own antiparticle, and that has very fundamental physics consequences. And in particular, it would help us to understand one of the cosmic mysteries, which is why the universe is here at all. Because we think in science that the universe started with a big bang, a state of enormous energy. We can change energy into particles and antiparticles, and the particles and antiparticles can annihilate back to energy. But somehow this process took place billions of times as the universe cooled down and expanded, and we are left in a universe which just has matter in it. What happened to the antimatter? We don't know the answer to that, but it's possible that there's a clue in the properties of neutrinos that would help us to understand this cosmic mystery. So it's considered one of the very important projects. Politicians understand economics far more than scientists do, but what's the economic worth of this kind of physics? Well, I think we can judge. There are two experiments currently being constructed, one in the United States and one in Japan, which are both at the giga-euro scale, and they are addressing one aspect of this problem. Double beta decay addresses a different and perhaps more fundamental aspect of it. This is the scale of the physics we're doing. It's a scale that tells you these experiments have to be done globally. We have to get the world together, just as the argon experiment is drawing the world together in a global argon experiment. We need to start thinking about a global xenon experiment if we're going to be doing physics at this scale. And this experience with argon is absolutely phenomenal. It's very important. There are some experiments being proposed, maybe at the 100 mega-euro scale. My expectation is that they're too small, and that we have to go to a much bigger scale. And then a dominant cost is how do you separate the xenon isotopes? And at the moment, that cost looks like being a giga-euro. And so the sign that you walked past as you came in today, which says distillation is the most energy efficient form of isotope separation, that's exactly what we need. Why are they so expensive? Well, xenon is very rare. The global production is something like 40 tons a year. The experiment we have to do probably needs a total of 1,000-ton years. And that means we need something like 10 tons of this isotope. But this isotope we need is only 10% of regular xenon. So if we were to use regular xenon, we'd need something like 1,000 tons. And that is just not going to happen because we're not the only people in the world who want xenon. It's only going to be feasible if we can make some concentration, extract just the form we need, and let the world use the rest of it. So distillation is a process that depends on the vapor pressure. And if you do distillation of things we're all familiar with, how to distill to separate alcohol from water, there the vapor pressures differ by about a factor of 4, and anybody can do this. They can do it in their basement. But in the case of these isotopes, the vapor pressure differences are very small. It's about 0.6% for argon. It's 0.01% for xenon. So can we do it? Well, we've taken the approach of can we actually see any separation in distillation for xenon? And so we've set up a distillation process to look for that, and this was motivated by the Aria ideas. We make a small still. It's exactly the same thing in principle to what Aria is, but it's very small. This is the still in our laboratory. It's small because we're not trying to produce anything. We want to do a measurement just to see, is it possible to make a separation? We looked at argon, krypton, and xenon, and this just shows you the mass spectra, the different groups of isotopes in these different elements. And what we measured are the concentration enhancement in the still between the top and the bottom. And the fact that you have the a straight line here with a slope says that the light elements here, 36, is concentrated at the top, and you get slight depletion of the heavy ones. That's more obvious. We did krypton, and here is xenon. And the fact that that slope is not a flat line is saying that we are separating xenon by a small amount, but in this small column. So where does this take us? We find, in fact, that our value for krypton and xenon are very consistent with what theoreticians tell us. This is different from the early measurements, which gave numbers of 0. And so we're very satisfied that it is possible now to start designing a real still to separate xenon. And so my conclusion, xenon can be separated by distillation. It's going to be very dependent on how concentrated we need to make it. I believe this is largely an economic argument. We can now start to look at this optimization. The physicists, first of all, have to look at what they really need. The area could, just as it stands, I think, make 20% enrichment. Normal xenon is 10%. It could double that. That's half of the economic benefit just from running the existing column. To go beyond that, and we almost certainly have to go beyond that somewhat, we have to look at enhancements, which could be some enhancement at the area facility. And then overall, the conclusion, fundamental physics has a long history of requiring large amounts of isotopically enriched materials. I see no end in sight to this process. There are new technologies, and it's important that we explore some of these. But a final point which I think is important in this discussion is the distillation separation gets more and more difficult as you get to heavier and heavier systems. And we can be fairly confident that it doesn't work for uranium. And that's a great plus, because with any isotopic separation, you have concerns about nuclear proliferation. We have no concerns with distillation. So it's a very good technology for that reason, for the economic reason, for the energy reasons. And so we look forward. We're at the very early stages of thinking about xenon, but it's looking very promising, and it's something for the future. And I'll leave it at that.